Good afternoon, or whenever you're watching this, physics friends. Today we're going to be talking about static electricity. We're going to be talking about how like charges repel, opposite charges attract, what gives something a charge. If you had something that's positively charged and you want to make something negatively charged, is there a way to do that? And we're going to talk about that today. So I've got a really great video from PBS that we're going to watch and go through and take some notes on. It's got some really great visuals, and let's get going.
The shock you get from a doorknob, that trick you used to do with a balloon to make your hair stick up, or of course a lightning strike, they're all governed by the same principle: static electricity. Static electricity occurs when an object obtains a net amount of positive or negative electric charge, creating an imbalance that wants to be returned to equilibrium. Its effects aren't always as dramatic as lightning though. Let's take two pieces of tape that are both stuck to a table. If you rip them both off the table and tried to stick them together,
this actually works, by the way.
Easy enough, right? But it turns out that they repel one another. But try this: stick one on top of the other, rip the pair off the table, then separate the pieces. They're no longer repelled, now they're attracted to one another. In the first scenario, both pieces of tape stole negative charges from the table, and since like charges repel, the pieces moved away from one another. In the second scenario, one piece of tape stole negative charges from the other, leaving the pieces with opposite overall charges, making them attract. Our study of electricity begins here, with basic observations about electric charges that hundreds of years ago sparked the imagination and innovation that changed our world forever. To understand electricity, you should start with an atom. Atoms contain charged particles, positive protons and negative electrons, and generally there's an equal number of each, meaning the net electric charge of the atom is zero. It's electrically neutral. In solid materials, protons stay fixed, but some electrons are free to move around. These moving electrons are called free electrons. They reside in the atom's outer shell as valence electrons, and are easily plucked off and carried around when acted upon by an outside force.
Now, we got a couple of things I want to get down in our notes. Electrostatics. That's when, maybe you've heard of the word static before in your English class, where you have a static character versus a dynamic character. Or if you're in sports, you've got static stretching versus dynamic stretching. In physics, we have statics and dynamics. Statics is the study of still things, things that are in equilibrium. Net forces and net accelerations equals zero in the x, y, and z directions. In dynamics, they don't have to. The same with electrostatics. That's when you have a buildup of charge that's standing still. An electron, that's a negatively charged particle. And it's the really important thing here as far as electrostatics is the electron is allowed to move. It's allowed to, those free electrons in the valence band, they're allowed to move. A proton is a positively charged particle. It doesn't move. Everything we're going to talk about today is kind of based on the fact that electrons can move, protons are stuck. Neutron, that's inside the nucleus, and that's a neutrally charged particle. Like charges, if they're alike, they repel, and if they're opposite charges, they attract.
How easy it is for electrons to move around depends on the material, and we describe the materials in the same manner that we do for heat transfer with conductors and insulators. Materials that are conductors, like copper, let free electrons move freely throughout the solid, while insulators, like wood, hold on to them tightly, limiting their flow. So we've got insulators and conductors with free electrons moving around in them.
All right, so those are our next couple. Insulators and conductors. I'm going to skip over this page here. I'll actually move it for your notes, so we'll just go right to this one. Insulator doesn't let electrons move around. Some common insulators are plastic, glass, ceramic, air. Air's kind of, and you see down below, it's an insulator unless you push hard enough. Like if you have enough pressure, which we call voltage in the electricity world, Rubber, wood, conductors, they do let electrons move around. Some really good conductors are metals. And some of the best metals are copper, gold, platinum. And you can kind of tell, like every wire that we've got is made of copper. You can get gold plated. I mean, we just don't put gold because they're really, expensive. People. And water. Sometimes some people think water conducts electricity, but water doesn't. Pure deionized and distilled water doesn't conduct electricity. It's the minerals and the salts that are inside of water that do the conduction. And you can kind of see in the periodic table over here where copper, gold, platinum, they're all kind of in this neck of the woods, which kind of gives them those free electrons to give and to receive.
But what causes these charged particles to move in the first place? The answer is an imbalance of electrical charge, when some part of an object has a different number of free electrons than another part. When we talk about an object having an overall negative charge, we mean that it has too many electrons. And when we talk about an object having an overall positive charge, we mean it's missing free electrons.
Yeah, one of the common misconceptions is that, if something's positively charged, it's got extra protons. Not really what it is. It's just missing electrons. It's like the idea that there's no such thing as cold. It's just missing its heat. The heat is left.
This imbalance can be created and resolved in lots of different ways. Say you have a glass rod that's electrically neutral and you rub it with a cloth. That physical interaction causes electrons to hop onto the cloth, leaving the rod with an overall positive charge. This is called charging by friction. Both the cloth and the rod began with a neutral charge, but after friction, the rod has a net positive charge. But whether the rod ends up with a net positive or negative charge depends on the materials that you use. The ancient Greeks actually rubbed fur against amber and discovered that the amber would then attract hair and feathers. Today we understand that the fur stole electrons during the process, giving the amber an overall positive charge, just like the glass rod. Now it's important to note that no new charges were created during this process. The overall charge between the two objects is still zero. This is known as the law of conservation of electric charge. It says that you can never create a net electric charge. Instead, charge can only move from one place to another.
Yeah, that's it. But it's kind of like the law of conservation of energy. Energy is neither created nor destroyed. Charge is neither created nor destroyed. You're simply moving it from one place to another. So we can never make electric charge. We just move it. We take it from someplace, give it to someplace else.
Now if we bring our positively charged glass rod in contact with another neutral rod, some of the negative charge, that is some electrons, will jump from the neutral rod to the positive one until both objects have the same distribution of charge. So now we have two rods that are both slightly positive. This is called charging by contact. When the two objects touched, charges move between them. Okay, so charges can move when different materials touch each other, either through friction or simple contact.
And this is called charging, in my notes, I think I label them as charging by conduction. That's by charging by touch. There's a way to charge something by not touching it, and that's what induction is. And she's going to talk about that.
Materials don't actually have to touch in order for their electrons to get all rearranged. Say you bring a positively charged rod close to a metal conductive rod, then the electrons in part of the metal rod will be drawn towards the positive rod. Now the side with more electrons has a negative charge, leaving the other side of the rod with fewer electrons and a positive charge. Do you know what we've done here? We've polarized the metal rod. We've redistributed the charge in order to create an imbalance of charge within an object that's still electrically neutral. Now imagine that we slice the...
So polarizing just means that you have one side that's positive, one side that's negative. Like water is polar because of the H2O, the way it's organized. There's a positive side and a negative side. Maybe you learned that in chemistry class.
It still hasn't touched the positive rod, but since we split it while an imbalance was present, we're left with one positive side and one negative side. This process is known as charging by induction, creating a net charge without contacting another.
So you see what happened? She brought this positive rod, and then the electrons were attracted over to it, which means that once they get drawn near it, then you can cut that, and then you have a separation. And in your notes, you kind of have the same idea, where you've got two spheres here. Bring in a negatively charged, so then the electrons, they aren't attracted to it, but they're repelled. So the electrons are pushed away to this side over here, and then you separate the two spheres. Once you've pushed them away, that's charging it by not, we didn't touch anything. We didn't touch this to give it electrons or take electrons away. We just pushed or pulled them through repulsion or attraction.
Other object. Now, if a charged object is connected to a much larger neutral conducting object, then the net charge gets redistributed so that the smaller object loses most of its net charge. How large an object are we talking about exactly? Well, how about Earth? The Earth's surface is a fairly good conductor in most places, and for our purposes, it can be considered neutral. So connecting a charged object to the ground creates a way for the charge to leak into the Earth, rendering the object electrically neutral. This is known as grounding. So let's say we repeat the previous experiment, but we bring a negatively charged rod close to our neutral one. The neutral rod becomes polarized, with a net positive charge close to the charged rod and a negative charge on the opposite side. But if we ground the metal rod, the negative charge is repelled by the charged rod, now have a place to go. The Earth. The negative charges scurry away, leaving the metal rod with an overall positive charge. Now,
electrons ultimately want to get as far away from each other as possible. So the best place to do that is to go to the Earth, because the Earth is huge. They can go to the Earth, spread themselves out, and get as far away as possible.
Our rod remains positively charged. This process required no contact between the rods, only a connection to the ground. Okay, so we've talked about how opposite charges attract and like charges repel. But how do we quantify those interactions in terms of equations and units? Well, we'll want to find the force on charged particles in newtons. But to calculate the number of newtons, we'll first need to measure the charge, denoted by Q, in units called coulombs. Since objects can be positive or negatively charged, Q can have both positive and negative values. For example, one electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. That means there are 6.24 times 10 to the 18th electrons for every negative coulomb.
Okay, so this is a couple numbers that are kind of significant here. A coulomb. 1 coulomb of charge. We knew about charge before we knew that the electron charged it. And it turns out that when we found the electron, and that was what was responsible for static electricity, we had to start counting them. And there was like 6.24 times 10 to the 18th electrons. So there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 18. I hope I did that right. Yes, I did. There's 6 quintillion electrons. And this is actually what 1 amp is. If you have an amp of electricity, that means that you've got 6 quintillion electrons passing by you every second. So this many electrons every second is what we call 1 amp in the electrical world. And the electron is just 1 over this. So how much charge does 1 electron have? It's 1 over 6.24 times 10 to the 18th, which they said was 1.6 times 10 to the negative 19th coulombs. So this is how we quantify charge. And we're about to talk about how much force is on charged particles, and we're going to need these numbers to do so.
Value, the charge of a single electron in coulombs, is known as the elementary charge, and it's denoted with a lowercase e. We'll use this notation a lot when talking about protons and electrons, since protons have a charge of positive e and electrons of negative e. Now that we have a way to measure the charge, we can calculate the force between particles. And the equation we use is very similar to the one we use with gravitation. It's just that instead of using kilograms to find newtons, here we're using coulombs to find newtons. Our equation here states that the force between between two charged particles is equal to the product of the two charges divided by the distance between them squared. And the distance is squared because, just like gravitation, when the distance between objects doubles, the force between them reduces to a quarter of the original value. And also, as with gravitation, this force has its own proportionality constant.
Now, we skipped over the unit on gravity when we were going through it, but the equation for gravity is force is equal to g times the two masses, mass 1, mass 2, divided by the distance squared. So it literally looks exactly the same as those two.
Its value depends on the medium that surrounds the charges. The vast majority of the time, the medium you'll be working with will just be air, or possibly a vacuum. And in both cases, the constant is 9 times 10 to the 9th coulombs. So when you multiply the rest of the expression by k, that gives you the result in terms of newtons.
All right, let's get this equation in our notes. This is Coulomb's law. Coulomb's law states that how you find the force of an object, it's directly proportional to the charge and indirectly proportional to the square of the distance. So you have F equals K times Q1 times Q2 over the distance squared. And F is going to be force, and it's going to be, the units are going to be newtons. Q is going to be charge, and the units are going to be coulombs, or C. D is going to be distance, and that's going to be in meters. You got to be careful. A lot of the problems that we do, they give you to in centimeters or millimeters, so you got to make sure that that distance is in meters. And this K we call Coulomb's constant. And it's just a number. It's 9.0 times 10 to the 9th. And it's newtons times meters squared over coulombs squared. Kind of a really funky units, but you'll see. I'm going to move away from her experiment, from her video right now, and just go into an example problem for you to find force. Now, example problem 1. It says that you've got two spheres. You have sphere A, which I'll put here. A has a charge of a positive 6 microcoulomb, so millionths of a coulomb. It's located near another charge, sphere B, which has a charge of negative 3 microcoulombs, and they're separated by a distance of 4 centimeters. See, there's that centimeters again you got to watch out for. It says, what is the force of sphere B on sphere A? So sphere B, these are oppositely charged, so these spheres are going to attract one another. And their force of attraction is going to be equal and opposite. It's Newton's first law. Every object, every action is an equal and opposite reaction. I think that's Newton's third law to be true, to be honest. So even though they have different charges, they can have different masses, all sorts of that stuff, but we learned that they have equal and opposite forces regardless. So to find that force, we're going to use Coulomb's law. So we're going to take Coulomb's constant, which is 9.0 times 10 to the 9th. And I'm going to put the units here in green, newtons, meters squared over coulombs squared. Just to show you kind of how this works. I may have to move it over because with all my exponents. First charge is 6.0 times 10 to the negative 6th coulombs. And you'll notice that I couldn't use microcoulombs because you see I've got coulombs in the denominator over here of these units. So then I've got negative 3 times 10 to the negative 6th coulombs. I'm going to divide by the distance, 0.04 squared, and that's meters. So now you can see that coulombs times coulombs are coulombs squared, and then meters squared cancels off right there. And when you do all of this, I've already done it already, so I know that the answer is putting it into my calculator. It turns out to be 100. 100 newtons of force. That's actually quite sizable, which is how you can get electrons moving so quickly. They're so very small, and you can exert really big forces on them. So there's 100 newtons of force. Now you might be saying to yourself, Mr. Hare, isn't a positive times a negative, isn't that equal to a negative? That's true. But remember, with forces, the direction is really important. So you could go through these and figure out what the negative means that it's like attraction, or the positive means that it's repulsive. I just think about it like these are opposite charges, so they're going to attract. So the 100 newtons is this way. What you cannot do, you can't put a negative 100 here, because in our parlance, a negative 100 means it's actually pointing the opposite direction, so you have to make sure this is a positive 100. So there's using Coulomb's law. This can get a little bit more complicated, and when you look at part B, it says that there's a third sphere that makes an appearance here. So you end up actually having a third sphere. It says sphere C. Sphere C comes down here with a charge of positive 1.5 microcoulombs, and it is 3 centimeters away. If it's, what is the new net force on sphere A? So what you're going to do is we're going to redo this equation down here, except now we're going to put in 6, but this becomes a 1.5. And my distance is not 0.4 anymore, it's 0.03. And when you run that equation, that will end up equaling 90. Again, I've done this beforehand, so I kind of know what it ends up equaling. 90 newtons. It's supposed to have 2 significant figures, but these are repelled. So this gets pushed this way at 90 newtons, and then this one also gets pushed this way at 90 newtons. So now you start to see a little bit of first semester making its way back in here. If A is being pushed to the right at 100 newtons and it's being pushed up at 90 newtons like this, you add these tip to tail to find your resultant. And so to find the resultant net force on particle A, you're going to do Pythagorean theorem, a squared plus b squared equals c squared. And that turns out to be 130 when you solve it. And then to find the angle, like what angle is this thing being pushed at? That angle is going to be the inverse tangent of 90 over 100, which turns out to be 42 degrees. So the net force is equal to 130 newtons at 42 degrees above the positive x-axis. So there, we got Coulomb's law, kind of merging 2 semesters here all at once with static electricity, how we can push and pull on objects.